Oh, hello. Well, welcome to a panel discussion on the use of P4 in NICs. So I think most people will be used to switches being talked about in the P4 community, but in a lot of cases, what people actually have in their desks or on their labs are NICs rather than switches. So there's increasing interest in how P4 fits into the world of the NIC and with edge computing and things like that. So we have here a panel to discuss the topic of NICs, programmable NICs, and the use of P4 in NICs. And in view of the special circumstances, we're doing a kind of low budget cast here. So I'm combining a role of being the moderator of the panel with one of the panelists. And I'm Gordon Brebner from Xilinx. And I'm very happy to have with me Mario Baldi and John Cruz, who are both at Pensando, who are kind of leading the way with programmable NICs at the moment. So together we're going to do short presentations first, and then simulating the audience, we'll have a lively Q&A session amongst ourselves. So we'll be managing to recreate a sort of 200-person panel discussion with 3 people. So that's our ambitious project here. So having said that, Mario, John, do you just want to quickly introduce yourself, do better than my introduction?
Yes, thank you. Yes, my name is Mario Baldi. I'm a distinguished technologist with Pensando, and at Pensando we have a P4 programmable platform, so I've been working with it, and yeah, we'll soon see what we'll talk about. John, please go ahead.
Thank you, Mario. I'm John. I've been with Pensando for about 3 years, and before that I have got experience with the P4 working with barefoot networks. So been working with close to about 5 years on P4.
Yeah, and for myself, I sit in Xilinx Labs, the kind of research part, the CTO office at Xilinx, and yeah, I've been involved in P4 more or less since the beginning, and we've been doing sort of P4 compilers, and also worked in the P4 language group quite a lot on sorting out P4.16 was one of our main agendas. So I'm pretty steeped in P4 world myself. So on that note, let me start sharing some slides, which I'll go through quickly. I'll just check with the other panelists if they can see them on their screens, which means we're probably good. So yeah, this is really a kind of more general backdrop, just to sort of introduce the topic of what we might mean by programmable NICs and how P4 might come into that, and I'll say a little bit about some of the previous research we've done on this topic. So this is my one slide simple introduction to the world of NICs for people who are sort of not acquainted, and no disrespect to particular logos on particular boards here. It's the same board with different logos. I've gone up a time scale from sort of DOM NIC to the basic, smart, and intelligent and programmable NIC. And I think, as everyone knows, you have a NIC card, which is a network interface card, and that's connecting the network side to the CPU side of the system. So that makes it slightly different from a switch. In the first place, switches have lots of network ports coming in and switching between them, whereas with a NIC, its main mission in life is being an interface to the processor. And some of the parameters I've just put there briefly. The 1-port NIC is kind of well known, and often the 2-port NICs. And then in different categories, you might have a larger number of ports, but it's nothing like a switch, which might have 64 ports or 32 ports or 128 ports. So it's a smaller scale object in terms of network interfaces, and there's a whole range of different line rates that it might go to. I put down at the low end, there's a 1 gigabit scale, up to today's high-end NICs of 100 gig, 200 gig, and going on 400 gig for the future. So the NIC's been evolving from being this kind of humble card that just does a job of connecting an Ethernet port to a desktop or a server, and gradually more intelligence has been put into the NIC over time, and that's why it becomes interesting as a programmable object that isn't just passing packets from the network interface to the CPU and in the other direction. So that's really why we're interested in the topic today, where there's not just non-trivial, packet forwarding as a switch, but I think you'll see from what we say today, there's all sorts of other things that might be going on, on a modern NIC card that are beyond just basic packet forwarding. So that's our simple landscape. And there's a very simple way of looking at this from a P4 point of view. And you have this provocative diagram, which is a kind of, can you spot the difference between what might be the well-known switch style architecture, as in PSA, the programmable switch architecture from p4.org, or a NIC style architecture. And the only change I've made is instead of a switch fabric, on the left-hand side, I've put a host CPU. So when someone started talking about P4 and NICs, the question was, do we have to do any work whatsoever? Is it just a case where sort of plugging in a CPU instead of a switch fabric? And it turns out the actual pipeline in the middle is the thing that's familiar. But then in the NIC context, we'll find ourselves putting other things round about it, rather than it just being a simple pipeline. For a simple NIC, this is probably a pretty simple architecture, but I'll show a couple of examples where things can get more sophisticated, and Mario and John will also be talking to that as well. So that's one viewpoint, and the other is there a difference between an endpoint, sort of computer attached network, and a middle box, which is in the network. And on one level, they're both the same thing. A middle box in the network is just some kind of server with network interfaces. So the kind of hope is we might get some reuse here between using P4 in the context of some end system versus some kind of in-network system. Obviously, a switch is a special case of a middle box. That here we're assuming it's got a smaller number of ports. So that's the kind of general landscape for our discussion on sort of NIC versus switch. How different are they? How much new work is there to be done? So one way this is in my kind of Xilinx Labs world, if you like. A kind of classification of increasing sophistication we've come up with for what we call adaptive NICs. And the type one is the simple case we all know about. There's the network on one side, and then application software and CPU on the other side. And there may be some standard offload functions, like TCP segmentation or something, that are fixed. But apart from that, it's a pretty straightforward pipeline from the network to the CPU. Then the type 2, which is what we were looking at first, is where you can put in some custom functions, and that's where P4 can start to come into play, instead of having some standard NIC pipeline, which can handle, say, Ethernet, VLANs, IP, some TCP offload. Is you can put in a P4 pipeline on the ingress and egress of that type 2 NIC, so it becomes a programmable object. So that's the difference between type 1 and type 2. And then, in my particular, Xilinx is an FPGA company, so we like building things in programmable hardware. Is in type 3, I've got this other direction going off at the side, which is where we're looking at having some applications in hardware, and that means you're looking at the payloads of packets as well as the headers. So if you like, the kind of vertical dimension, as in type 1, type 2, is the data plane, header processing stuff. This thing going off to the right is where you start terminating transport functions, for example, and instead of having packets of data, turn it into streams of data, or maybe data in memory, which can be handled by applications. And again, one can just have standard functions put here, for example, TCP, or for example, RoCE for storage, RDMA over Ethernet. And then the step to type 4, which is the kind of the thing we're looking at currently in Xilinx Labs. Xilinx Corporate, in terms of its NICs, is already at type 3 in terms of productization and connecting application hardware to the network pipeline. Here we're looking at what does it mean to customize the transport functions. So for example, instead of just having a fixed implementation of TCP, can you describe a transport protocol which goes beyond just packet processing? You need to include things like what's the congestion control algorithm, and how is reassembly and segmentation done, and stuff like that. So that's a kind of ongoing research area. But in our world, it involves connecting things across to application hardware. And I think when we carry on with Mario and John, we'll also see this notion of taking the basic packets and changing them around into messages or streams, or just read and writes to memory is something in the advanced NIC world that's very important. It's not just passing packets up the line to a CPU, it's how you reassemble data. So that's a kind of little taxonomy that we like to use. In terms of earlier work, and I've spoken about this at a previous P4 workshop a few years ago, I think, is this was our little cartoon block diagram that at the time we were using 40 gig Ethernet NIC, and the idea was having an ingress pipeline with P4 and an egress pipeline, but also in between. And this is the kind of sideways motion I mentioned, having application function acceleration, where that could be specified using either C with high-level synthesis or RTL, hardware design language. But the idea was, to put this in between and have, other data paths that aren't just, the ingress path and the egress path. So if you screw your eyes up a bit and look at my little green blob diagrams here, these were 4 use cases we kind of demonstrated, and this was 2 or 3 years ago now. Is the top left one is the normal SmartNIC case, where you have stuff coming off the network to the CPU and coming back out again. The next one at the top right was the one that people thought I must be a madman for doing, which was the network interface isn't actually involved, but instead we have 2 virtual machines communicating via the NIC. So at first sight, people say this is madness. Why aren't these communicating via the hypervisor? Why are you going all the way down to the NIC and back up to the virtual machine? And the answer was, this is a much lower and predictable latency path than doing it via the hypervisor. Using DPDK, in fact, to get down to the NIC, it strips away a lot of the software overhead. So in fact, it turned out to be significantly faster and predictable latency to do the virtual machine communication this way. Then my sort of beige box in the cartoon get involved in the bottom left. Is there? It's a deep packet inspection example, where the payloads of packets have been looked at, and the kind of idea here was most things don't actually go to the CPU. It's kind of orchestrating what's happening, and that's the thinner black arrows. But the thicker arrows show the data is not actually going to the CPU. It's staying in the NIC, and the CPU is kind of orchestrating what's being done to the data. So it still has a hand in it. And then the kind of final coup de grace, if you like, in the bottom right is, the CPU is reduced to just configuring things and being there in case of disasters. And so for video transcoding, you actually have data streaming off the network, going through some video codec, and then going back out again. So, these were our experimental use cases, and it's to loosen up people today for thinking of the NIC as something that's a bit more sophisticated than just this kind of ingress data path and egress data path, and that there's far more interesting other data paths that can come up, and this will also feature in our other presentations and discussions. So that's what we were playing with up till a couple of years ago, and as I say, the Type 4 NIC and what does it mean to do programmable transport is currently our main research focus now that this stuff is being productized. So this is our current playpen, if you like. Separately at this event, you can see a round table talk described towards an open P4 programmable hardware platform. And this is the kind of 1-slide summary of what we're using. And this is based on the kind of latest Xilinx Alveo cards, which have 200 gig ports on them. And because, you know, the raw hardware is generally hard for people to use, and programming FPGAs from scratch is hard, we're providing this kind of infrastructure on top, where what we've done is on the Ethernet MAC side, put a wrapper around the sometimes hard to use standard CMAC is 100 gig MAC block that comes with the Xilinx FPGAs, putting these little green adapters to simplify the interface. And similarly on the CPU side, putting a little adapter around the QDMA is the current version of Xilinx DMA to the CPU. So the idea is, you know, where these big black arrows are, it's a simplified data stream, and users can do their experiments or construct new hardware systems in the user region. And, you know, that's where we have a P4 playpen, because we can put P4 pipelines you know, into that user region, or other, you know, add-on externs, you know, either on the side of the pipeline as with your PSA externs, or in the pipeline as kind of fully contributing externs, for example, a traffic management function or things like that. So that's my current playpen, and we're kind of open sourcing this so the community hopefully has a faster route from, you know, P4 to programmable hardware, you know, FPGA-based NICs. So that's my object of choice at the moment. And on this final rather busy slide, one of the things that's been going on in the P4 community, which is a kind of backdrop for what we're talking about today, is, you know, paralleling the PSA programmable switch architecture, which has a p4.org spec out for over a year, is a portable NIC architecture. And this is a group of people which is very open to new contributors, by the way, looking at what might be needed or desirable for a PNA architecture. And, you know, this is where many of the issues I've alluded to, and I think Mario and John will allude to, you know, when I switch over to them shortly, is, you know, exactly, you know, what do we mean by the ingress and egress pipelines? You know, what are in them? Do we need different functions from the switch architecture, or is it broadly similar? Virtualization, you know, having, you know, virtual ports from the CPU side, for example, and or virtual ports from the network is important. How we model the collection of network ports, you know, in PSA, for example, like mysteriously, you know, 64 ports are aggregated and disaggregated. You know, it doesn't show up in the P4 except as metadata. So how do we deal with multiple ports in the NIC? Is it easier or is it simpler? And, you know, do we actually have a switch hidden inside the NIC, for example, or, you know, is it just pipelines? And we'll be discussing that, you know, as we go on today. And then there's the fact we now have a host CPU, you know, on the side. That is a new feature. You know, in PSA world, you know, CPU is just there for the control aspects and kind of on the side, so to speak. But for us, by definition, in the NIC, the CPU is a mainstream player in that, you know, it's expecting to get data going to and from it. Then there's this kind of, you know, beyond just packet forwarding, which is P4's current strength. You know, do we move into protocol processing, if you like, you know, where we do things like TCP termination and handle segmentation and things. And, you know, is my notion of a type 3 NIC covered, you know, if we have other stuff, you know, which isn't, you know, packet processing, how do we integrate that into P4 world? And, you know, the kind of aim was not to have a completely separate spec for PNA from PSA. The hope is, you know, that we can have a modular approach to specifications, if you like. You know, so there's a lot of common modules and components and externs and things, and then you kind of build PSA and build PNA out of those. But yeah, one thing we're pretty sure about already is current P4 is not sufficient for describing all the things we might want to do in a NIC. So the question is, you know, how much do you extend in P4 as a domain-specific language, or how much do other things come into it? So on that note, I'll stop my sort of brief introduction. You know, that's my kind of view of the NIC world, but also, you know, what's been going on in p4.org for PNA. So this talk's been a kind of combination of moderator introduction and your Gordon's pet topics. So on that note, I think it's a great time. I'll yield the sharing here, and you'll pass it over to Mario and John.
Okay, thank you very much, Gordon. So yeah, let me start with saying that here we stretch a little bit the title and the topic of this panel, and we are actually presenting use cases that sort of motivate an evolution of P4, so some new functionalities within P4, and as Gordon was saying, also an evolution of the PSA. And some of this is generic, not necessarily specific of programmable NICs, but some of it is specifically targeting programmable NICs. And so what are we going to talk about? As I said, we're going to talk about use cases. We'll go through 2 use cases. One is TCP connection tracking. I will talk about it, and the idea is to show how, for addressing that use case, we can benefit from having P4 writable tables that can be modified within the P4 program. And then John will talk about another use case, or actually a couple of very tightly related use cases, which are generic segmentation offload and large receive offload, which instead are very typical applications of NICs. And those will help showing the value of having an architecture that's not exactly what the PSA is today. And before getting into this, I'll give you a quick overview of our little but I guess we're talking about a similar thing. This is the platform that we used to implement those use cases. And this platform supports the extensions we are talking about. And so I want to first of all introduce it briefly. So the Distributed Services Card, or DSC, is a programmable platform that has a PCIe connector, interface, so it can be installed in a host. And then it has, on the other hand, 2 Ethernet interfaces. We have 2 models of the card. One has 25 gig interfaces. The other one has 100 gig interfaces that then can be operated at different speed. They can be broken down to multiple lower speed interfaces. Now, because this platform can be plugged into a PCI bus and has Ethernet interfaces, can be used as a NIC, but it is not just a NIC. I mean, it is much more powerful and versatile. Actually, we like to say that only 5% of its essence and identity is the one of the NIC. The rest, the remaining 95% is additional functionality and value and potential that this card has. And all of these comes from this chip that you see here, this ASIC, for which I'm going to provide a quick overview now. But this ASIC has a very interesting architecture. It's very flexible, and it can be used in many different ways, packaged in different ways. So packaging it into a host adapter is just our first step. But again, this architecture is much more versatile and powerful. And let me take a quick look at that architecture. So this diagram is representing that ASIC that we were seeing in the card. And as we said, it has a PCIe interface as well as 2 Ethernet interfaces. And then it contains a packet buffer to store packets that are received through the interfaces, or to store packets before sending them out from the interfaces, with all of the traffic management features that one might want to use to support quality of service, so multiple queues, sophisticated scheduling. Then the ASIC includes a P4 programmable data plane, which is a set of P4 programmable pipelines, which can be used to process packets in a very efficient way. But that's not the only processing that we can do in that ASIC. We also have a ARM complex with a number of ARM cores and a number of service processing offloads which are specialized hardware components, which are targeting functionalities that are particularly resource intensive, that require a significant amount of memory or CPU, like encryption or compression or calculation of digests. So we can leverage those for those specific functionalities. And all of these processing elements have access to a memory, which is pretty sizable. We have two versions, 4 GB and 8 GB. And so this memory can be used to store state from the process. So this can give you an idea that the range of applications that we can cover here is pretty wide and goes way beyond the ones of a NIC. But again, this can be used as a NIC, and some of the use cases that we present are related to NICs. And the NIC can be a starting point to use this platform. And then as the user wants, they can add more functionalities and get more value, get that 95% extra value from this platform. And again, this is just a very high level introduction, but you know, if you want to have a few more details, you can watch the talk that I gave in the context of the P4 Expert Roundtable, entitled Programmable Data Plane Architecture for the Network Edge, which describes this architecture and shows how it can be used to implement a couple of use cases. So now, talking about use cases, let's delve into the use cases that we want to consider now. The first one, again, is a motivation for enhancements to P4. And as I said, the use case we want to talk about is connection tracking, TCP connection tracking, which means basically reconstructing the state of a TCP connection by observing the packets that are traveling through the card, through the device. And the idea is to make sure that the endpoints of the connections are in the proper state, in legitimate states. And this can have various applications. For example, from the security point of view, you might want to protect one of the endpoints from the injection of packets that are not consistent with the state of the connection. So for example, packets that have wrong sequence number and try to exploit weak implementations of the TCP that would not handle them properly. So this is clearly a stateful operation. We need to keep the state of the connection, and especially we need to update it whenever we process a new packet. So we get a new packet, we process the header, and based on that information, we update the state. So how can we implement this in P4? Well, the way we implemented it on our platform is by using a table that has information that can be updated dynamically. And this is something that we don't see in this slide. This is the declaration of the table. We just see, you know, we declare a table with a key that is the identifier of the connection. Obviously, this is just a snippet of the code, but these are the essential pieces of information, the 5 tuple. And this table has one action, which is called TCP session state info. And there is where now we are going to see the enhancement that we are using here. So if we look at the parameters of this action, we see that we have some regular parameters that can be used by the action, read from the table and used by the actions, and some other parameters that have this annotation @__ref, that is saying that those parameters can actually be modified by the action, and then they get written back into the table. And obviously, the way we use this is, now I included a little snippet of the action body. We use those parameters. This is one of the modifiable parameters, which is the acknowledgement number of the direct direction of the flow, of the forward direction of the flow. And here we see that, first of all, we check that the acknowledgement number in a new message, in a new TCP message we are processing, is coherent with what we have seen before, with what we have stored. And if so, we are going to update the information of the valid acknowledgement number that we expect in the forward direction. So here we see again another extension, the possibility of having one of the action parameters on the left-hand side of an assignment operation. So this is not, what we have just seen is not available in P4, in standard P4 16. Does it mean that we cannot implement connection tracking? Of course not, we can still implement it. We will resort to registers. So again, this is just an example, a possible example implementation. We declare a bunch of registers where we are going to store the state information for the TCP connection that we need to update, instead of storing it in a table as we did before with all of the information of the connection. Here we create multiple registers for the various pieces of information. Then our table looks the same, at least as far as the table declaration. But when we go and we look at our action to process packets and modify the state, that action obviously has only the part of the session state, of the connection state, that doesn't need to be modified packet by packet. And then in addition, it has an index that allows us to map the connection to an entry in the register, because registers cannot be accessed through a key like the table can. And so the idea is, at this point, our action is going to go and take every single register, find the value of the state that we are interested in evaluating and possibly modifying, and then it goes and writes back into the register. So sure, we can implement the same functionality with standard P4 16, but when we compare this to implementation, I would say the one with registers is a bit more cumbersome, more complicated, less legible. The code is less compact. We have all of those registers. We don't have all of the information belonging to the connection in one table, which is easy to read. But not only is it easy to read, but it's also easier to handle from the point of view of mapping it onto hardware. So when we have this table with all of the fields there, we might be able to more efficiently allocate that table in memory, in one big continuous part of the memory, while it might be more difficult to optimize the allocation of the separate registers. Especially the separate registers, each one have a discrete width, which we might not be able to exploit. It also have a limitation on the depth, and so we might not be able to use them efficiently. Now, on the other hand, of course, having writable tables come at a cost, because we have a number of challenges. We have, first of all, to ensure that reads that come after writes get the right data, the data after it was modified. And this is not easy to handle. It comes at the price of potentially performance, and for sure the price of complexity. So for example, in our platform, we support this, but we have specialized hardware to propagate the writes. So these require a more sophisticated design. Moreover, this is even more challenging when you consider having multiple pipelines, and you have to keep the consistencies across multiple pipelines. You're going to have multiple copies of the table, or if you allow a table to be used in different stages, you'll have multiple copies. You have to propagate those stages. These are challenges, but it might be worth addressing them, because writable tables provide a certain level of flexibility over registers. The other limitation is you cannot map these tables on TCAM, because updating TCAM requires a complex procedure that cannot be done online. Now, when you use registers, you don't have these challenges, but the reason why you don't have these challenges is because basically you're working around them, and you are doing that by introducing constraints. Registers are specific hardware devices, not general memory, and so Of course, it's easier to handle the read after write on those specific devices, but those specific devices have limited size, they have limited parallelism, and normally they have limited scope. They cannot be used from anywhere in the pipeline. So there is a limitation, and we believe that although it made sense in the initial version of P4 to make life a little bit easier and not allow tables to be writable, time might have become mature to enable this. And our platform, in fact, does it. So it's obviously something that can be done. So at this point, I'm going to leave the floor to John, who is going to talk about a second use case.
Okay, thank you, Mario. Alluding to what Gordon said, one of the key differences as a NIC is that not only we receive it's just not just packet transfer between ports. Here we need to get packets from ports or network ports and then transfer it on to the host. And from the host that wants to send a packet, we need to take it and send it out on the interface. And Gordon had pictures of type 1 and type 2. So kind of like saying that some standard NICs, they offload some functionality which takes the load out of the CPU and gets the network part to do the work. So here I'm going to talk about two cases, which one of them is called as generic offload, generic segmentation. And following that, I'll talk about large receive. So some of them know generic segmentation also as TSO, TCP segmentation. So basically to the host, the network adapter provides saying that, okay, I have a huge buffer. So the host doesn't have to create packets or buffers of smaller size. The host will say, okay, here is my buffer or a large collection of buffers, in case where he wants to scatter gather operations, and says, transmit this packet, and it gives that to the NIC as a single request. Now, a traditional NIC will go ahead and say, okay, I'm going to take these buffers, and depending on the segment size, it does the segmentation. So there are two parts that are involved as part of this segmentation. One is to take this bigger buffer or buffers, find out based on the segment size and chop them into smaller buffers. And then the next part is what a network functionality would be to update the IP ID, IP length, IP checksum, TCP checksum. If it's TCP, if it's UDP, they call it generic because it can work for UDP. You can do Geneve offloads. So you need to update multiple layers of values. So all of them needs to be done as part of the generic segmentation offload. Next slide. So this is the same thing that I said in a pictorial format, saying, okay, I have here represented one big buffer with a header, and how as GSO, this big payload is segmented into multiple smaller packets. And then these are the ones that go on the wire. Next slide. So as in case of in a typical, a PSA, the input is actually a packet. But here, the input is part of what they call as a transmitter descriptor ring. It's a bunch of pointers with header, with pointers and size of how much to DMA. So it is not really, there's no really a parser as such. So a P4 program typically starts off with a parser which receives a packet, parses it, and then based on whatever it has parsed, creates metadata, looks up table. But before even we can do that, here we just have a bunch of pointers and the size of data that has to be DMA'd. So what we really need is another kind of a construct here, or a few constructs here, which will help us segment or create these fragments of this bigger packet and then DMA it down into smaller packets down into the packet, into the network portion of it. So I have kind of split it into two functionalities for GSO. One is the host functionality, which if you want to implement in software, which your driver would do, or we could even bake this into a very special hardware and call this as part of the NIC, the GSO offload. But keeping it programmable means that when newer protocols come in and you want to provide this kind of offload, having it programmable as a P4 programmable part, it's easy for people to go ahead and make changes to them. So if you notice here, this is just a generic functionality, which is saying, okay, find out how much has to be sent, have the right set of pointers, and keep sending or DMAing the amount of data that needs to be DMA'd for every buffer. Also DMA the header associated with it. So you're going to DMA two parts, the header and the packet. Together you form the packet. Next slide. So the network functionality, once let's say you have the packet fully formed, the smaller packet, then you can parse the packet, identify how many IP layers are there. Then now you can go ahead and start updating the length field, the TCP checksum. If any UDP is there, UDP checksum, UDP length, IP ID. If it's a TCP, the sequence number also has to be updated as part of the segmentation, because that refers to the size of data that's being sent. So that is the start of the data. So all that update has to be done as part of the network functionality. So what I have described here as English, so a pseudocode. So this is the main control portion of it, which says, okay, I have a TX ring that needs to get applied, and the TX is done. Then I move on to the buffer. Okay, so here's a TX ring, applied a TX ring. So this is the first table, the TX descriptor, where we receive the address of the descriptor. We read the descriptor. So here again, I have borrowed from what Mario referred to as, instead of using registers, usually with a descriptor ring, you have a producer index and a consumer index, rather than creating a separate register to indicate here is where my set of consumer indices and I have an index into it. It makes sense for me to put the entire action parameter as one table, right? So this is a table with just producer indices and consumer indices. And this is just a normal producers per consumer problem saying, okay, if I have something to consume, go ahead and consume it. So update my consumer index. If I have nothing to do, I'm done. So I have highlighted another extern, or my first extern here, which is ringing a doorbell. So one of the things that NICs host, the way it talks to the network portion is by ringing doorbell, saying that, okay, I have data to transmit, or when the network component is done, it says I'm done. It posts an event in the completion queue and it rings another doorbell. So we should be able to describe this as an extern. One might say, well, we don't need to add it as part of the standard architecture. Let each hardware provide an extern. But we kind of find a need for these kind of externs. I'll be going through more of these externs later, like an extern like doorbell, which we think is something that the architecture should provide. Next slide. So this is the second table where we're going to look at based on the consumer index, the buffer. We read the information about the buffer, and then we loop through the buffer and segment it. And here we have highlighted two parts. One is a while construct, which is not available with a standard P4 functionality. It can be emulated by other operations, but the main extern that I wanted to highlight here is a DMA extern. So as a NIC, if we are going to talk to a host, we may have need to transmit packets, in which case we need to DMA from host to the network. And on packet reception from the network, we may have to DMA packets back to the host. So we kind of see a need for this new extern for DMA. So I'll introduce more externs later. So meanwhile, I can look at another use case. Next slide, Mario. So the next use case is large receive offload. It's the complement of the GSO. So in GSO, we took a bigger buffer and segmented into smaller TCP packets or smaller packets, and then we sent it out on the network. Here, as a network functionality, as you're receiving packets, it is possible that you might get consecutive packets, and rather than interrupting the host for every packet, you could put those packets together, form a larger buffer, and then send that packet to the host. So a couple of things the LRO, the large receive offload functionality involves is that it has to put all these packets in sequence and update the sequence number, update the TCP header, because now it is carrying a bigger packet. Once it's done, if we have allocated a specific LRO buffer, if the buffer is complete, DMA the entire buffer to the host. Let's say we have not received enough fragments, enough packets to complete the buffer. We need a timer here to let us know that we are done. We can't keep waiting for newer packets to arrive. So we need kind of a timer to let us know we are done, to notify the host that a new packet has been received. So Mario, next slide. So this is the pictorial representation of an LRO. So you have receiving packets with headers and segments. So based on IP ID, and in case of TCP, you have the TCP flow information based on S port, D port, protocol, SIP and DIP. Together, you can come and arrive at saying, okay, this is the flow. You can provide LRO buffers for multiple flows, or you can just provide for a certain type of a flow. And then you can reconstruct the payload. Kind of helps with the host in not having to be woken up very often, and gives a larger buffer to work with rather than smaller buffers to work with. Next slide. So here are some of the constructs that we think are required to be added to the standard P4. The next couple of slides goes into details of them. So one of them is a doorbell that I mentioned to kind of let the program start. So rather than having a parser start the program, in this case, we'll need a different kind of a notification to start the program, and a kind of a way by which when the program is complete, the P4 program is done, a way by which we can also let the host know that we are done with what our work has been assigned to us. And as far as we need DMA operation ways, we clearly looked about saying, okay, we need to DMA packets back and forth, timers to let us know that, okay, an event has happened because we want it to be awoken some number of milliseconds or nanoseconds later. Stateful memory, this goes back to, again, registers. Do we want to use registers, or do you want to use action parameters as writable so that you can keep track of the state of, okay, where was what was the last memory that was sent? Where is the next buffer that needs to be sent out in case of transmission? Reception, what was the last segment ID that I received? The current segment that I'm receiving, does it match with the previous segment that I could just coalesce them? Or is it another one where I have to flush the old segment and take this new segment as the start of a new LRO packet? Next slide. Again, so this is just going into details of what a doorbell requirement is. Like traditionally P4 programs, we start them based on the incoming of a packet. So the first beginning of a program is the ingress parser. So this is kind of a component that is even before a parser. So where we could actually trigger it based on an event. And likewise, when an event is done, when the P4 program is done, it may need to post an event back to the host saying, I'm done with this event. So we're thinking of two constructs. One is to start the program execution. The other one is an extern to ring a doorbell saying, I'm done with my execution. The next extern that we're looking for is DMA. So DMA, you may want to DMA memory to packet. This is for transmission. And as I mentioned, your support for gather, which means that you're not given a single buffer which you want to transmit. You're given n different buffers, and you want a segment, and a segment that you want to send can actually straddle two buffers. So you want DMA memory to packet. Packet to memory, this is mostly for reception. There are also other encryptions and other offloads that Gordon also alluded to, where you could support so other features on the side on a NIC, such as encryption or compression. So in which case you may have a requirement to DMA from one memory location to another memory location. And there's also where you may want to DMA. In case of P4, we talk in terms of PHV, which is the metadata that is sent in the pipeline. And you may want to, some metadata that we may want to also notify that or write it back to memory. So notice that this is not metadata that we're constructing it to a packet and sending it out on the network, but this is metadata that we want to DMA from the pipeline to the host. This is primarily to update the TX and the RX descriptor rings. The next construct is, Mario, timers. Again, so this is to, let's say LRO case. We keep receiving packets, and at some point of time we have not received any packet. You want to say, okay, I'm done with this coalescing whatever I could coalesce, and I want to send it back. So we're looking for externs to support starting of a timer, and also like to start at a particular P4 location, a particular program, a particular table lookup, on a timer expiry. So this is kind of saying that we would like to see a doorbell mechanism, which kind of says, okay, on a doorbell, this is the first table to be looked up. On a expiry of a timer, this is the first table to be looked up. So these are some new constructs that we're looking for. Mario, you would like to continue?
Yeah. Okay. So yeah, to conclude, what do we learn from these use cases? Can P4 be used for a host attached device? Yes, of course, but probably we need an architecture that is not exactly the PSA. It's an evolution of it. I mean, we have a different situation than the one of a switch. As John was saying, parsing is not always done. Parsing is optional, and we need different triggers than the arrival of a packet to start the processing. And John gave us a great example of usages of timers, of doorbells. We need to be able to prepare multi-packet data, like exactly the use cases that John was showing us, which means we need memory to do that, where we can put those temporary pieces of data that have arrived. And then once we have memory, even just the memory of the host, we need to be able to access it. And the table construct is one possible way. John was showing us how with the table you can access the descriptors of the rings, but there other ways are needed. And we need also a way to transfer data like a DMA. And also, taking all of these considerations in mind, we have proposed a possible architecture for the PNA, the Portable NIC Architecture. And as Gordon was mentioning before, there has been some work in this respect in the architecture work group. And this proposal actually goes along the line of what Gordon was saying. Hopefully we are going to be able to leverage what we have done in PSA. So in our view, the architecture for PNA could include sort of the PSA. If we look at this compared to the other proposal, the example that Gordon was giving before, now here we have a packet buffer in addition, which might be important to handle packets that are received or they have to be transmitted and need to be queued for QoS. And then especially we have pipelines that are not front-ended by parsers. And these fulfill the purpose that John was describing, being able to start a P4 processing without a packet arrival. And we use those in the interface towards the host. And then in addition, we envision we might need some specialized processing modules, like also Gordon was talking about before. This is probably an important element to have. In Gordon's presentation, we saw it in the various types of NICs already. We're seeing that, and then of course modules to transfer data. For example, DMA, but in general to transfer data towards the host through the host interface, which might be a PCI interface. So again, now I don't want to go into much details of this architecture, but this is a little bit a point of arrival of this talk that John and I gave. We wanted to show a couple of use cases that justify working on an architecture that's different from the PSA, and possibly also adding some constructs to the P4 language to support the use cases that we have spoken about and other use cases that are typical of NICs and not only.
Okay, thanks, Mario and John. Yeah, maybe if you unshare that we can get bigger pictures of ourselves. Yeah, we've used up quite a lot of the time, I think, though it kind of interlaced with each other, but there's a little time for some discussion at the end. I mean, a couple of things I'd say. I enjoyed your presentation there. It helped to reinforce my own thinking on this. I mean, one of the aspects, having match action tables, you can update from the data plane. I mean, I think quite a few people have come across this topic already. You had your example. I mean, Mac Learning is another example that comes up, where you actually want to update things from the data plane and your higher level applications. So I think, there's quite a lot of hardware technologies that actually support that. As you say, it can be non-trivial depending on how sophisticated your table is. That, if it's a fairly simple binary CAM, you can get away with doing data plane updates. I think, that particular and beyond NICs, has a lot of popularity. I think this has been discussed in the language community before. I think usually the pushback comes because of the implementation problems. Are there enough targets apart from software targets that could implement it? So that was one thing that very much resonated with me. And the other one, though, in John's piece, is the need for your events that, other than packet arrival events, and that's something I've also been looking at separately. And some work it's with Steve Abanius and Nick McEwen at Stanford and Gianni Antici in London. Is it actually came originally from looking at traffic managers, where we wanted things like a queue is full or almost full, signaling an event to the pipeline, to indicate that something needed to be done. And then we realized that started off as a special case for us, but a more general notion of event processing in an architecture, and that would include things like timeouts and events like you showed. And we did a little prototype last year. In fact, the Stanford CS344 class were innocent guinea pigs for a paper we had at Hotnets, in that we did a prototype event driven and they did some applications as their class projects to do that. So I think, again, that's something else that's very much in the wind, not just for NICs, but in the P4 community. So I think your talk brought out that very interesting two things that are lively topics that people would like to do in terms of pushing P4. Yeah. And I think the final, go ahead, Mario.
I'm sorry to interrupt. If I'm not mistaken, in that paper of yours that you mentioned at the Hotnet, you also show how having events allows you to go beyond certain limitations, like you can work on loops and some level of iteration that if everything is based just on packet processing cannot be done, right? If I'm not mistaken.
Yeah, that's right. It's when you kind of move on from just packet forwarding or packet processing to protocol processing, if you like. I noticed very controversial on one of your slides, a while loop. That's a much debated P4 topic. Should loops ever get into the language, etc. But yeah. One of the main issues you alluded just in your match action tables, which can be updated, then you've got state problems and read-write conflicts, is it also gets much worse when you start adding arbitrary events, because it means instead of having one point in the system where things happen, packets arrive, is suddenly if events are firing in different places, then you have this consistency problem for shared state. So that's something we talked about in the paper, but didn't really have a solution for in the paper. We could just see that it was adding complexity. So which is of course the problem with adding these features to P4, which is a pretty stark language with a stark implementation, is to actually get beyond packet forwarding. And I think most of us would like to do that, and it's very important in the NIC context. So I think just thinking about NICs is a starting point for these bigger debates in the P4 community. And as you said, Mario, that proposal you showed on the last slide is a kind of elaboration. I had a similar one, which I should credit Andy Fingerhut, by the way, who provided that block diagram to the PNA group that I selfishly claimed as my own in my slide. So, but when you stand to 60,000 feet above, it's the same issues being addressed. I think in both of our presentations. Yeah. And the short answer is NICs are a more complex use case because there's more different things going on. As Switch is trying to get rid of packets as fast as possible. So right. I think that's a good convergence.
Yeah, in NICs, on the one hand, having fewer interfaces and dealing with less traffic, you you have less performance issues. I mean, performances are not taken to the extreme as in switches, which is good from the point of view of writing P4 programs, because you can do more on your packets. But on the other hand, as you said, you have the additional complication of having also the host part to handle, and that's not just the packet interface. And but by the way, talking about switches and NICs, one of the differences between the diagram that you were showing, and as you said, Andy had proposed, and the Fingerhut had proposed, and the one that we were showing about the potential PNA, one of the differences was the lack of a packet buffer. And so in a way, the packet buffer put there makes the NIC being a switch, which I think is in line with some of the use cases that you were showing, right? You were showing some use cases where traffic was coming in and out. I mean, in the type of NICs, I think type 3, or you had, sorry, not type 3, but those 4 examples that you had.
Yeah, the green blob diagrams.
The green blobs. The 2 at the bottom had traffic coming in from one interface and going out to the other one directly. So it was a kind of switch functionality. So you do see a value of such a functionality within a NIC.
Yeah, it's funny you should mention that. And in a way, when you prepared that PNA proposal you just showed us, suddenly I had a great sense of relief that it actually showed a switch there. So if what was going on in our experiment show with the green blob diagrams is because we were working with an FPGA, we were kind of building, direct point-to-point connections for different experiments, so for a particular experiment, we knew the data paths we wanted, and we were kind of building that in logic. Now, the interesting that's happening, that was our Xilinx Labs prototyping, and that was a couple of years ago, is Xilinx now has a productized version of a smart NIC, based on some of all of the ideas we had back then. And when you look at the internal architecture of that, guess what? There is actually a little switch. So, it has, the network ports are coming into it. It also has like virtual channels coming from the CPU side going into it. And in our case, it even has accelerators coming off the side. So, if one's familiar with a traditional big metal switch, you put a little header on the front of packets as they go through the line card and through the switch fabric and back out again. It turns out, in the actual, the smart NIC architecture that Xilinx has developed, this is the proper engineers, not folks like me. It actually does have a little switch quite explicitly there for doing these kind of mappings between the ports, the CPU, and also transferring over into memory world from packet world. So, as I say, I like to see it there, not just because it's kind of cute, almost saying PSA is a subpart of PNA, which is world domination for the NIC, but also in terms of how people are implementing sophisticated NICs, and I think the same applies to you. We're finding you do actually have a little switch fabric there. So if we can harness PSA thinking for that, that's a good thing for me. So I'm glad you brought that up.
Not only, but that switch in the NIC comes handy also for that other green blob that you had, where you said people thought you were mad, but today it's extremely important, which is switching traffic between VMs. I mean, that's really a very important application also for.
There are some use cases, as you said, Mario, where people are actually running network functionality, virtualized functionality on VMs. And so when traffic comes in, it has to go to a VM, get switched somewhere out there, and then come back out, or between VM, you want to send traffic. And people are trying to move functionality as much as possible from the host down to the NIC so that they can free up the host for it to use the CPU cycles. So as much as functionality can be moved down from the host down into the NIC, that's good.
Yeah. In some ways, we're kind of shortchanging ourselves by still using the term NIC, because your network interface is a bit, it doesn't describe remotely. A few years ago, I tried to turn it inside Xilinx into NAC for Network Accelerator Card, but I was overridden on all sides because NIC is the household term. But I think when people think of NIC, they think of something pretty simple. That as I hope the audience appreciate, you have been exploring this today, just saying, look how complicated it might get, and is getting in real NICs these days.
Yeah, absolutely true. That's in fact what I was saying at the beginning about our platform. That's really calling it a NIC is well, maybe we'll think about it. And PNA could have another acronym, since we haven't had it. It's not out yet, so
yeah. There's still time.
Yeah.
So I suppose maybe one final point I was keen to ask you about just before we finish is, I noticed in your architecture you had the ARM cores, and on the FPGA we also have ARM cores. It is just to explore with you. A lot of the time, on NIC ARM cores are just used, for control plane stuff, slower stuff. But in this context of the NIC becoming more powerful, are you seeing your ARM cores for doing, fast path or medium path data plane processing, or more just for control functions?
Yeah, no, absolutely. We definitely use them. We tend to call it exception path because we try to do as much as possible on the P4 data plane, because those pipelines are really very, very efficient. But for complex processing, or for example, in the other talk that I gave in the context of the P4 roundtables, one of the use cases I was showing was the one of a stateful firewall, and sometimes you need to perform certain processing that it's too complex to do in the P4 pipeline. So you do it for the first packets or few packets of a flow, and then you handle the other ones with the flow cache in the pipeline. So yeah, absolutely. And I think one great advantage of a platform where all of these aspects are tightly integrated is you can easily move packets and or information between those different processing elements, including the offloads, right? You also had in your platform accelerators. I mean, we call them processing offloads, but at the end, I believe we are talking about the same thing. So when those elements are tightly integrated, then the potential is really huge, what you can do, because you can really combine them easily.
Okay, yeah, that's kind of concurs with my own thinking. So yeah, I think we've got a lot of convergence here on the panel. We haven't had a heated debate, I'm afraid. I apologize to the audience for that. We haven't been at each other's virtual throats, but hopefully it indicates to people, that you might think at first sight NICs are easier than switch, and they may have less performance requirements than a switch, but they're far richer in terms of capabilities, and there's a whole new evolving world which the P4 community can look at. So on that note, I encourage people, there is this PNA, until we change the name maybe, to working group within p4.org. So if people are interested by this topic, I'd ask you to look out for that. It's meeting fairly regularly at the moment. But on that note, let me thank Mario and John for joining in a really interesting discussion. It's a favorite topic of me, and I'll thank myself for being on the panel as moderator. But yeah, hopefully you've appreciated this in the audience, and we can't meet in person on this occasion, but yeah, I've enjoyed it a lot. So thanks everyone.
Same here. Thank you very much, Gordon, for your double job that you did here.
Yeah, I'm being paid twice for this assignment. Okay, thanks everyone.
Thank you.
Take care.